And this form, in this form, we have -5. This is not desirable. This is bad. We don't. We must positive value in constraint because x greater than or equal to 0. Okay, -1 multiple to this constraint. We have -2x1 minus x2 plus x3 greater than or equal 5. Okay, and transformed to a equal form. Simplex method solve a standard problem. A standard problem is equal constraint, have an equal constraint. Okay, x this form change -2x1 minus x2 plus x3 minus s2 equal to 5. We have r and minus I. This is bad. We don't have basic matrix. We have minus I. R is 1 minus 2 minus 2 and minus 1 1 and 1. This is R and I is -1 0 0 minus 1. This is minus I and it's bad. Okay. Pay attention, please. This can be accomplished by introducing a slack variable and by simple manipulation of the constraint and variables. See chapter 1 for details. If R contains as an identified matrix, then an immediate basic feasible solution is at hand. By simply letting B equal to I, and since B greater than or equal to 0, then B inverse B equal to B greater than or equal to 0. Otherwise, something else must be done. A trial and error approach might be futile if the do you understand this? We have two cases. Easy case is the canonical form of maximize, and bad case is the canonical form of minimization. See this problem? Consider this constraint. This is a less than or equal. X3 is a slack variable. X3 is a slack variable. This form is less than. This is x4. xb when simplex, x3 and x4 x3 and x4 is x1, x2, x3, x4, zj minus cj, right hand side. x1, 1 minus 1, 2, 1, 1, 0, 0, 1, 4, and 1. x3 and x4 is a basic variable, and I is basic matrix. x3 and x4, B inverse B, I, 4 and 1. We have xb, basic variable, 4 and 1. I multiple to 4 and 1 is equal to 4 and 1. This. xn is non-basic variable. Non-basic variable is 0. This is. Bad case. This is good. This constant one is good. Less than. This is a less than. But constant 2 is bad. Why? We have greater than, and this is 3. If we have minus 3, this is good. Multiple minus 1 in constant 2. But this is 3. We have minus 2x1. We have minus 2x1 plus 3x2 plus 2x3 plus minus x5 equal to 3. This is bad. We have minus x5. And you know, in chapter 1, see that when x1, it didn't, in this problem, x1 is unrestricted. x1 is unrestricted. x2 and x3 is equal or greater than to 0, but x1 is unrestricted. What is mean? x1 can be negative or x1 can be positive, but x2 and x3 must be positive or 0. But x1 can be positive or negative or 0. This is x1 is unrestricted variable. When we have an unrestricted variable, we change this variable to two variables, x1 plus minus x1 minus, and this is this form is change x1 in this formulation. You see this? And say x1 plus minus x1 minus, and x1 plus and x1 minus is greater than or equal to 0. Do you know why?
No.
No? Okay. Uh, for illustrate this, wait please. Do you see this page?
Yes.
Okay. We have, this is a standard for, excuse me, must be paint. Okay, this is a standard for. We have common, stand, okay. In canonical form, we have minimum 6 Rx greater than or equal to 0, x greater than or equal to 0. And the maximized form is Cx Rx greater than or equal to 0. X in standard form, we have minimum or maximum form is 6 x b equal b and x greater than or equal. This is a standard form. For use simplex method, we must have a standard form. We must be this form for use simplex method. In this method, in this standard form, x must be greater than or equal to 0. Okay, when please wait. When, for example, we have minimum x1 minus 2x2 subject to plus x3 subject to 2x1 plus x2 greater than or equal to 5 minus x1 plus 2x2 minus x3 equal to minus 6. x1 minus x2 plus x3 less than or equal to 1. x2 and x3 greater than or equal to 0. We have this problem. We have changed this problem to a standard form. For a standard form, we have minimum x1 minus 2, x2 plus x3. This is must be changed. 2x1 plus x2 minus s1 equal to 5. This is negative. We don't have negative value. We don't, it must be positive value. Minus 1 multiple to this, we have x1 minus 2x2 plus x3 equal to 6. And x1 minus x2 plus x3 plus s2 is equal to 1. x2 and x3 equal greater than or equal to 0. x1 is unrestricted. This is not a standard form. A standard form have minimize or maximize 6 or x equal to b, x greater than or equal to 0. But x1 is not greater than or equal to 0. This is unrestricted value. For solve this problem, x1 change to x1 plus minus x1 minus. x1 plus is positive or 0 and x1 minus is positive or plus to 0. For example, x1 is 5. Okay? For example, x1 is 5. Okay, x1 plus is 5 and x1 minus is 0. This is a positive and this is a 0. Okay, if we have x1 equal to minus 5, then we have x1 plus is 0 and x1 minus is 5. x1 plus is 0, correct in this constraint, and x1 minus is positive 5 and x1 is minus 5. This change, this transformation solve my problem. If x1 change to x1 plus and x1 minus greater than or equal to 0, because if x1 a negative value, then x1 plus is 0 and x1 minus is negative value. For example, -3, x1, b -3. Okay, x1 plus is 0, x1 minus is 3, and we have 0 minus 3, but x1 is greater than or equal to 0, x1 minus is greater than or equal to 0. Do you understand this?
Yes, yes.
Okay. Okay, this change solve my problem, and x1 change to x1 plus minus x1 minus. x1 in this constraint changed to x1 plus minus x1 minus, and in this constraint to constraint changed to excuse me, x1 changed to x1 plus minus x1 minus, and in this constraint x1 minus x1 plus minus x1 minus, and this is a standard form. This is a standard form, and this is a LP, linear programming problem, and I can use simplex method. Simplex method used for a standard form. Okay. This we have this one. Okay, consider the following constraint: x1 plus x2 minus 2x3 less than or equal to -3, minus 2x1 plus x2 plus 3x3 less than or equal to 7, x1, x2, x3 is greater than 0. For distance, we'll change this constraint. We have minus x1 minus x2 plus 2x3. This is minus 3. We must minus 1 multiple to this constraint. Okay, we have x1 minus x1 minus x2 plus 2x3 less than change to greater than 3, and we have this constant minus x1 minus x2 plus 2x3. This is a greater than or equal. Then we have minus x4 equal to 3. This is a this is an easy case. We have minus 2x1 plus x2 plus 3x3 and less than 7. Then we have minus x5 equal to 5. This is a standard form. Okay. Artificial variable. Oh, we have we have minimum or maximize 6 x less than or equal b, x greater than or equal to 0. Minimum c, b, c, n. Minimum c, b, c, n, x, b, x, n, and r x plus I s equal to b, x greater than or equal to 0. X change xb, xn, basic variable, non-basic variable. S is a slack variable, or xb basic variable, in non-basic, S is slack, or is artificial variable. What is R? See this? After manipulating the constraint and introducing slack variables, suppose that the constraints are put in the format Rx equal to B, where R is an M multiple n matrix and B greater than or equal to 0 and B is a M vector. Furthermore, suppose that A has no identified submatrix. If R has an identified submatrix, then we have an obvious starting basic feasible solution. In this case, we shall resort to artificial variable to get a starting basic feasible solution, and then use the simplex method itself and get rid of this artificial variable. What does this mean? R is artificial variable, S is slack variable. In your book, Rx, Rx less than or equal to B, change to Rx plus XS. This is S, okay? This is a slack variable. This is a slack variable equal to B. Suppose that bad case. This is an easy case. Suppose that we have bad case, Rx greater than or equal to B, Rx minus Is or Ixs equal to B. We don't have basic. We don't have basic variable. We don't have basis. We change this constraint to this constraint, XR or R. XR or R, artificial variable, equal to B. This XR is artificial variable, and B must 0. XOR B must 0. Why? XOR must 0, must be 0. Why? You know, this is because the relationship is equal. Because the relationship is equal. This relationship is equal. This relationship is equal. This is equal. We don't have any XOR. This is equal. We don't have any XOR. If this relationship equal to this relationship, XOR must be 0. Are you understand? Do you understand this? I can't hear your sound. Do you know this?
Yes, yes.
Okay. Therefore, this relationship is equal, and if relationship 1 equal to relationship 2, XOR must be 0. This is artificial variable. This is a XOR is artificial variable. Okay. Please pay attention to next page. Consider the following constraint: x1 plus 2x2 greater than 4 minus 3x1 plus 4x2 greater than or equal 5, 2x2 plus x2 less than or equal 6. This is easy case. What? Constraint 1 and constraint 2 are bad case. Okay, we change this constraint x1, x2 and minus x3, constraint 2 minus x4 greater than minus x4 equal to 5. Constraint 3 is a case less than or equal to 6 plus x5 equal to 6. This constraint is good. X5 is a basic variable, but x3 and x4 doesn't good. So we only need to introduce two artificial variable x6 and x7 in these two constraints. Introduce two artificial variable x6 and x7. This is equal. This is a equal relationship, but we add this constraint x6 and add this constraint x7. x6 and x7 is artificial variable. Artificial variable must be 0. Okay? Please see this film. Pay attention to this film.
In this video, we are going to see two-phase method. Before we see the problem, let us see the basic points. The first one is minimization type of objective function. See, in two-phase method, whatever may be the type of objective function in the original problem, only the minimization type of objective function is used in the two-phase method. If we get any maximization problem, just convert the maximization into minimization by changing the sign. Look at the second point, constraints. For greater than or equal type constraints, just subtract slack variable and add artificial variable. That is minus S1 plus A1. Okay. So for lesser than or equal to type constraints, just add slack variable only. Here we need not introduce any artificial variable. So this is the procedure regarding constraints which involves greater than or equal to and lesser than or equal to. The next point is it has two phases, phase 1 and phase 2. Okay, for phase 1, we are going to follow the same algorithm which we applied for simplex method, but with the revised objective function. Okay, so initially we have to prepare the initial simplex table for phase 1 and apply the usual simplex method till the optimality is reached. Okay, at the end of the phase 1, check whether the objective function value is 0 in the optimal table. If yes, go to phase 2, or else just conclude that this problem does not have any optimal solution. Okay, in phase 2, after finding the optimal table, from the optimal table, you have to proceed phase 2 by replacing the original value of objective function. Okay, let us see in detail along with a simple problem. Look at the problem, two-phase method. So minimization z is equal to 10x1 plus 6x2 plus 2x3. Okay, here we have got minimization problem. If we get maximization problem, the first step is we need to convert maximization into minimization by changing the sign. But here we need not worry about that because we have got minimization problem. Look at the constraints. Subject to the first constraint is minus x1 plus x2 plus x3 greater than or equal to 1. Next one, 3x1 plus x2 minus x3 greater than or equal to 2. x1, x2 and x3 greater than or equal to 0. Look at the second point, constraints. For greater than or equal to or equal type constraints, just subtract slack variable and add artificial variable, that is minus s1 plus a1. Okay, so for lesser than or equal to type constraints, just add slack variable only. Here we need not introduce any artificial variable. So this is the procedure regarding constraints which involves greater than or equal to and lesser than or equal to. Here we have got greater than or equal to. So we need to subtract slack variable and add artificial variable in the first constraint as well as for the second constraint. Now I am going to form the canonical form of the given problem. First is framing the canonical form. So minimization z is equal to 10x1 plus 6x2 plus 2x3 subject to first constraint minus x1 plus x2 plus x3. Here we have got greater than or equal to. So subtract slack variable and add artificial variable is equal to 1. Second constraint 3x1 plus x2 minus x3. Subtract slack variable and add artificial variable is equal to 2. And x1, x2, x3, s1, s2, a1 and a2 greater than or equal to 0. Now we have to add the values in the objective function. The objective function is 10x1 plus 6x2 plus 2x3. No, just add 0s1 plus 0s2 plus a1 plus a2. So here we have got two slack variable. No, for slack variable we have to give 0 value plus 0s1 plus 0s2. For artificial variable value is 1, that is a1 plus a2. So this is the procedure to frame the canonical form of given problem. The next step is just copy the values as it is. That is the first constraint and second constraint must be as it is. Take the value as it is, and when we take the objective function, take only artificial variable, that is a1 plus a2. Just leave all other values. This is called as a revised objective function. Minimization z is equal to a1 plus a2 subject to take the constraints 1 and 2 as it is. Minus x1 plus x2 plus x3 minus s1 plus a1 is equal to 1. Second constraint 3x1 plus x2 minus x3 minus s2 plus a2 is equal to 2. And x1, x2, x3, s1, s2, a1 and a2 greater than or equal to 0. With this information, we can start initial simplex table for phase 1. See the initial table. This is the format of initial simplex table format. That is CJ value, basic variables and cost of the basic variables solution. Okay, so first we have to write the basic variables x1, x2, x3, s1, s2, a1 and a2. x1, x2, x3, s1, s2, a1 and a2. Values of the basic variables. For CJ, we have to take 0 for all the values except artificial variables. Look at the revised objective function. Here we have only artificial variables a1 and a2. So assign 1 for a1, a2 and for other variables put 0. So x1 0, x2 also 0, x3 0, s1 0, s2 also 0. For a1, a2 1, 1. Now frame the initial table for two constraints. For the first constraint, basic variable is a1. Okay, A1 value is 1. Okay, second one is A2, right? A2 value also 1. Now fill all these values. See the first constraint, minus x1. No. So minus 1 plus x2. Put 1 plus x3. 1 minus s1. So minus 1. No s2, no. So 0. A1 value 1. No A2. So 0 is equal to solution 1. In the second constraint, 3x1. So x1 value is 3. X2 value is 1. X3 value minus 1. S1 value 0. S2. So minus 1. No A1. So 0. A2 value is 1 is equal to solution 2. Okay, now we have to find the Zj value. In order to find out the Zj, just multiply the cost with each and every element and add the second value to find out Zj. Let me show the calculation. For the first one, 1 into minus 1, minus 1 plus 1 into 3, 3 is equal to plus 2. For the second value, 1 into 1, 1 plus 1 into 1, 1 is equal to 2. In the same way, we need to find Zj value for each and every element. x1 2, for x2 also 2, for x3 0, for s1 minus 1, for s2 also minus 1, for a1 1, for a2 1. Solution is 3. Okay, after finding Zj value, now we need to find Cj minus Zj values. Cj minus Zj. Okay, Cj value is 0. So 0 minus 2 minus 2. 0 minus 2 minus 2. 0 minus 0, 0. 0 minus minus 1 is equal to plus 1. 0 minus minus 1 is equal to plus 1. 1 minus 1 is equal to 0. 1 minus 1 is equal to 0. So we have got Cj minus Zj value. After finding Cj minus Zj values, just check the optimality condition. For minimization problem, the optimality condition is all the Cj minus Zj value must be greater than or equal to 0, which means we need to get 0 or positive value. Look at the Cj minus Zj values. Here we have got two negative values. So we didn't reach the optimality. So we have to proceed further until we reach the optimality. Okay, in order to proceed further, we need to find the key row and key column and key element. Okay, in order to find out the key column, select the most negative. But here we have got type, that is minus 2 for x1 and minus 2 for x2. So we can select any one, either x1 into minus 1 by 3, 0, plus 1 into 2 by 3, 2 by 3. Next value, 0 into 0, 0, plus 1 into minus 1, minus 1. Next one, 0 into minus 1 by 3, 0, plus 1 into minus 1 by 3, minus 1 by 3. Next one, 0 into 0, 0, plus 1 into 1, 1. So after finding Zj value, now we need to find Cj minus Zj values. Cj minus Zj. Cj 0, Zj 0. So 0 minus 0 is equal to 0. Next one, 0 minus 4 by 3 minus 4 by 3. Next value, 0 minus 2 by 3 minus 2 by 3. Next one, 0 minus
Hanım
minus
nasıl gidiyor?
is equal to plus 1.
Okay.
Next one, 0
No
minus
screen.
minus 1 by 3 is equal to plus 1 by 3. Next one, 1 minus 1 is equal to 0. Now we have got the
Okay.
Cj minus Zj values. Now again check the optimality condition. For minimization problem, the optimality condition is all the Cj minus Zj must be greater than or equal to 0, which means we have to get either 0 or positive values. But here we have got negative values. So we didn't reach the optimality. We need to move further. So in order to move to next iteration, we need to find the key row, key column and key element. In order to find out the key column, we have to select the most negative. So which one is most negative? Minus 4 by 3 or minus 2 by 3. So which one is most negative? Minus 4 by 3 is the most negative value. So this will be the key column. So x2 is the key column. Now we have to find out the key row. In order to find out the key row, select the most positive. In the solution column, we have two values now. Which one is most positive? 2 by 3 or 5 by 3? So 5 by 3 is the most positive value. So this will be the
where was film cut from? Where was film cut from? Do you see film?
Yes.
Okay. Excuse me. Okay.
key row. A1 is the key row, X2 is the key column, and 4 by 3 is the key element. Now we have to prepare second iteration. In the second iteration, X2 will be the entering variable and A1 will be the leaving variable. So instead of A1, we have to enter X2. X2 value is 0. Okay, so X2 is the entering variable and A1 is the leaving variable. Now we can proceed iteration 2. Iteration 2, basic variables are x1, x2, x3, s1 and s2. We need not write a1 because a1 is the leaving variable. No, so we need not write a1 again. Coefficient for these basic variables x1 0, x2 also 0, x3 0, s1 0 and s2 also 0. In the second iteration, we need to find the new values for row 5 and row 6. For row 5, look at the previous iteration. X2 will be the entering variable and A1 will be the leaving variable. So instead of A1, we need to write X2 here. So X2 coefficient value is 0. So X2 coefficient value is 0. Okay, so in order to find out row 5, look at the previous iteration. Key element. So 0 divided by 4 by 3. For second value, 4 by 3 divided by 4 by 3. For x3, 2 by 3 divided by 4 by 3. For s1, minus 1 divided by 4 by 3. For s2, minus 1 by 3 divided by 4 by 3. So the new value is for x1, 0. For x2, 1, for x3, 1 by 2, for s1, minus 3 by 4, for s2, minus 1 by 4. For solution, 5 by 4. Okay, now we have to find out row 6. For row 6, there is a simple formula. So as we did in the previous iteration, you can follow the same procedure. Okay. So x1 value is 0. For the new value, the formula is old value minus key column value into row 5 value. See the first one. The old value is 1 minus key column value is 1 by 3 into new row value is 0. The answer is 1. For x2, old value is 1 by 3 minus key column value again 1 by 3 into new value is 1. The answer is 0. For the third one, old value minus 1 by 3 minus key column value 1 by 3 into new value 1 by 2. The answer is minus 1 by 2. For S1, old value is 0 minus key column value 1 by 3 into new row value minus 3 by 4 is equal to 1 by 4. For S2, the old value is minus 1 by 3 minus key column value is 1 by 3 into row 5 value is minus 1 by 4. The answer is minus 1 by 4. For solution, the old value is 2 by 3 minus key column value is 1 by 3 into row 5 value is 5 by 4. The answer is 1 by 4. Now we have to find Zj value. Okay, for Zj value, 0 into 0 plus 0 into 1 will get 0. For second one, 0 into 1, 0 plus 0 into 0, 0. The answer is 0. For x3, 0 into 1 by 2, 0 plus 0 into minus 1 by 2, 0. For S1, 0 into minus 3 by 4, 0 plus 0 into 1 by 4, 0. The answer is 0. For S2, 0 into minus 1 by 4, 0 plus 0 into minus 1 by 4, 0. So the answer is 0. So now we have got Zj values. Now we need to find Cj minus Zj values. Cj minus Zj values. 0 minus 0, 0. 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 See, after finding Cj minus Zj value, just check the optimality condition. For minimization problem, the optimality condition is all the Cj minus Zj values must be greater than or equal to 0. So here we have got zeros. So we have reached the optimality. So after reaching the optimality, just check the important point as I said earlier. See the last point. At the end of phase 1, check whether the objective function value is 0 in the optimal table. Look at the optimal table. See the optimal table. This is the objective function values. These values must be 0 at the optimal table. If we get any values instead of 0, then the problem has no feasible solution. But in this case, we satisfy the condition. We got 0 values in the objective function. Now we can proceed further. Now we have to go for phase 2. In the phase 2, just write the values as it is from the optimal table, but accept the Cj values. For Cj values, we have to take the value from original problem. See, here we have x1, x2, x3, s1 and s2. Right, as it is. x1, x2, x3, s1 and s2. Okay, but the Cj values are 0 in the optimal table. But here we have to write the original objective value. See the problem. Look at the problem. x1 value is 10, x2 value is 6, x3 value is 2, s1 value is 0 and s2 value is 0. So take all these values except artificial variable. So we have taken artificial variable in the phase 1, but for phase 2 we have to take all other values except artificial variable. For x1, 10, x2, 6, x3, 2, for a1, a2, 0 and 0. Basic variables are x2 and x1. x2 and x1. So x1 value is 10. So put 10 here. x2 value is 6. So 6. For all other values, see the previous table, enter the old value as it is. For x2 column, 0, 1, 1 by 2 minus 3 by 4 minus 1 by 4, 5 by 4. Right as it is. 0, 1, 1 by 2 minus 3 by 4 minus 1 by 4, 5 by 4. For the next value also, write as it is. 1, 0, minus 1 by 2, 1 by 4, minus 1 by 4, 1 by 4. 1, 0, minus 1 by 2, 1 by 4, minus 1 by 4, and 1 by 4. Okay, now we have to find Zj values. For Zj value, 6 into 0, 0, plus 10 into 1, 10. The answer is 10. For x2, 6 into 1, 6, plus 10 into 0, 0. The answer is 6. Next one, 6 into 1 by 2, plus 10 into minus 1 by 2. The answer is minus 2. Next one, 6 into minus 3 by 4, plus 10 into 1 by 4. The answer is minus 2. Next one, 6 into minus 1 by 4 plus 10 into minus 1 by 4. The answer is minus 4. The solution, 6 into 5 by 4 plus 10 into 1 by 4. Answer is 10. Now calculate Cj minus Zj value. Cj value is 10. 10 minus 10 is equal to 0. For x2, 6 minus 6 is equal to 0. Next one, 2 minus minus 2 is equal to 4. Next one, 0 minus minus 2 is equal to plus 2. Next, 0 minus minus 4 is equal to 4. Now check the optimality condition. The optimality condition is a minimization problem. All the Cj minus Zj value must be greater than or equal to 0. So we have got all positive value. So now we have obtained optimality. So the optimal solution is 10. So the x1 value is 1 by 4. X2 value is 5 by 4. Optimum Z is equal to 10. Now we can check the answer by applying these values in the objective function. Look at the problem. The objective function is minimization Z is equal to 10x1 plus 6x2 plus 2x3. Right here, minimization Z is equal to 10x1 plus 6x2 plus 2x3. x1, x2 and x3. x1 value is 1 by 4. x2 value is 5 by 4. For x3, 0. And Z optimal value is 10. The objective function is minimization Z is equal to 10x1 plus 6x2 plus 2x3 must be 10. That is 10 into x1 value 1 by 4. So 1 by 4 plus 6x2 value is 5 by 4 and plus 2x3 value is 0 is equal to 10. 10 into 1 by 4, 10 by 4 plus 6 into 5 by 4, 30 by 4 plus 2 into 0, 0 is equal to 10. 10 by 4 plus 30 by 4 is equal to 40 by 4 plus 0 is equal to 10. 40 divided by 4 will get 10. 10 plus 0 is equal to 10. This is the way to cross-checking the value with the objective function. Thank you. Hope you all understand this video.
Okay. Do you have any question? Okay. Enough for today. For today is enough. Goodbye.
زينب خليت تنزلنا هذا الفيديو بالمجموعة.
Do you have any question?